Okay, folks, let's get started. The plan today is you're going to do a little work. And if you know what's going on, you're going to talk to the people that don't. You're responsible for the people next to you. And if you don't know what's going on, you're responsible to back the people next to you who seem to know what they're doing. Right? So please, this is an exercise, and I'd like you to develop some of the stuff before I take it up. So please get some work done. Right? And let's start. We have an object, let's say, I don't know, ball, solid sphere, that rolls downhill without slipping, okay? There is friction here, so no slipping on this side. But then, pay attention please, it rolls without slipping, and then when it gets down here, it hits a frictionless surface. Okay? So, this is going to drive me crazy. There's so much noise coming from this door. It's insane. Yeah. It's like a constant hum in the back of, I'm wondering what's going on. So, Josh, good on you for making it. If you know somebody who cannot make it today or you have to leave early, I want to see you Tuesday, right? Because this is important. Everybody? Rocket people. Right. Okay, so this thing rolls down until it gets here. When it gets here, it hits a smooth, frictionless patch. Okay? How high would it go up this hill? Right? So that's the first question. Another variant on this is it hits a spring of some sort where there is no friction on the surface, and how far will it compress the spring? Maybe we'll do that in, second iteration. A really important problem is this one. Okay, you have a cylinder, and the rope is wound around the cylinder, and now you have a mass here, and you know that the mass is big enough to bring everything up this way. What is the acceleration of the mass? Right, and you go over here, you've got, Egyptian technology. No offense, man. Right, so you're sliding stones on logs. Right? And there is no slipping anywhere. There is enough friction to make sure nothing slips. This could get interesting in that what? We could say, what is the limit of the force you can apply before something slips up here or down there or whatever. It could be really interesting. Okay? We're only going to do the benign version today. All right? The final is coming up. We have to leave some stuff for the final. All right? ECEs, you know what I'm talking about. Yeah. Okay. So we need to know the acceleration of this log, of this stone that we're trying to move somewhere. So, do you have any questions on this? I'm not going to write stuff down. That's a waste of time and energy and ink. Right? If you need to know what's going on, it's review the video that is going to be posted soon. Right? I posted all 3 videos so far that we've done. Anyhow, so do you have any questions about what's going on? This guy is going to go down, go that way, and how far up will it go? This is standard problem, kind of, rolling with something there. And, we have that guy. Okay. Do you want me to do the yo-yo for you first? Yo-yo may be a good thing to do first, okay? Let's just do the yo-yo first. I'm going to take a little bit of space here to do the yo-yo problem. Right. So yo-yo looks like this, and we'll do it 2 different ways. So what is a yo-yo? An object that has rope wound around it, and you just unravels like that. So the object is usually a cylinder of some sort. So cylinder, and what I'd like you to do is find the acceleration of the cylinder on the way down. It has mass m and radius r, and this is just rope. Okay? So begin here, please. 1, 2, 3, 4. So first step is, for this yo-yo, I'd like you to draw the free body diagram. So in the first approach, approach A, you have translation plus rotation about center of mass, right? So what should I have? We have to honor both aspects of the motion in that we have sum of forces to indicate, to show what the center of mass is doing. And then we have sum of torques about the center of mass. So in the first approach, approach A, rolling motion is seen to be what? A combination of translation of center of mass plus rotation about center of mass. Okay? So write down those three equations that you will need for that. Okay, let's say 1 minute. Okay? Full vector form, whatever. Right? So we said that in approach A, we have two things going on. One, sum of the forces in the y direction equal to MAY. And I've got tension plus mg equal to ma. Let me draw my forces on there. I do not want you to draw a new diagram. This one will suffice. We have only two forces. It's a simple problem. We've got mg this way, and we've got t that way. Okay? All right? It's kind of a bit of a puzzling problem, but it's really easy. And you pick down to be positive if you want. Forces, we choose straight lines or straight vectors for positive, negative. We say then that mg minus t is equal to ma, and that's macm, right? Center of mass. All right? So two unknowns are what? Tension and A. It looks complicated, but it's not that bad. Okay? Again, in approach A, we have translation plus rotation about center of mass. So second line should be sum of the torques about the center of mass equal to ICM alpha. And in this approach, I have the only thing that exerts the torque about the center of mass is not this guy, T. So you have T times R equal to ICM alpha. All right? Yeah? Okay, guys? Now, three unknowns. A is unknown. We got A, we got T, and we got alpha unknown. Two equations. Third equation is what? Because this is rolling motion, there's no slipping for sure because it's a rope. We say ACM is alpha R. And then our standard technique for solving torque problems, standard, right, is you plug in into the torque equation, this guy here. You bring in alpha from here in terms of A, and you bring in T from here in terms of A. T becomes something in terms of A. Alpha becomes something in terms of A. You have one equation, one unknown. All right? So when you solve that, what are you going to get? Quick? Wow, you're ahead of me, okay? I was hoping for something else before that. If I solve stuff here, what am I going to get? ACM should be mg over what? M plus ICM over r squared. When you solve this, you're going to get that, okay? And whatever that is. So 2/3 g. If it's a cylinder, you probably get 2/3 g, whatever it might be. What is the tension equal to? You can figure it out, okay? All right. So what do you have to do? I mean, I said cylinder. So I is, again, no mystery. This comes from the substitution, solving for one unknown, which is ACM. You get that. If you have any questions about this, I'll do it for you. But I'd rather not have to do that right now. Okay? This is something you can figure out on your own. Just a matter of math. Right? So you will go home and do this. All right, folks. So A is that. Fine. Good. And then you can find T from whatever. Okay? What's approach B then? In approach B, in approach A, we say that rolling motion is a combination of translation of center of mass plus rotation about center of mass. In approach B, we take torques about the point here, and that point is the point where the wheel or whatever is in touch with the surface that it rolls on. Surface kind of, momentarily the speed of that point is 0. That can act or will act as a momentary pivot, and we say that in this approach B, we have some of the torques about B is equal to IB alpha, okay? And what exerts the torque about B? Not T, so just mg times R equals to IB alpha, okay? It looks a bit different, but, well, so alpha, and now, instead of three equations, three unknowns, let me label them. Equation 1, equation 2, And equation 3, you combine them in this fashion, you get this. Here, one equation, one unknown. We're done. It's a very powerful approach. Right? So alpha is equal to mg r over I bottom. What is I bottom? ICM, it's parallel axis theorem. ICM plus the translation term, mr squared. So alpha is equal to mg r over ICM plus md squared. It's r squared in this case. And what I want is A. A is ACM, is alpha r, and I'll divide by r squared, okay? I'll be, people watching video, I won't do it there, there's no room. I'll be dividing by r squared, both sides, both top and bottom. I end up with what? mg divided by m plus ICM over r squared, okay? I'm mixing up r's, small and big, same thing. All right. So 1 minute to absorb that, make sure you're okay. Half a minute to wake up. This problem now, we have something that is going to roll downhill. We're told that. But then it's going to hit a frictionless patch. What does it do on a frictionless patch? So rolling, rolling, rolling. As soon as it hits it, what is it going to do? Pay attention. The object is rolling. Guys, rolling, 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 rolling. So here, it's rolling. What do we know about it here? If it's rolling, enough friction to make it roll, and this is kind of a smooth thing here to accommodate the ball. Okay? So when it's rolling, pay attention. V at this point is equal to omega r. So VCM is omega r. Why? Because it's rolling. All right? When it hits the frictionless patch, what's the first thing that's going to happen? It's going to start to what? Slide? If you don't think it's going to slide, put your hand up. There's a few weirdos in the classroom. Right? People don't think that's going to slide. Why? What's wrong with you? How is it going to roll on ice? You are absolutely correct. Right? So yeah, nothing is going to happen. Why? Because it has V and it has omega. These are the conditions for rolling. When does V change? When there is a force. When does omega change? When there is a torque. No force, no torque, V will continue to be equal to omega r. This object will roll on ice. Isn't that fantastic? Right? So it will roll on ice. So it's rolling, rolling, rolling. And then what's going to happen up here? Guys. Yeah. Oh, you're saying stop. I don't know about that. That's really interesting. Well, see now, this is a bit tricky. Okay? What do we need to slow it down? Force. Force will slow it down. What do we need to slow down what do we need to slow down the translational speed? V is affected by A. We need a force. Forces, right? What do we need to change the angular speed? Force changes the ACM, or dictates the ACM. Right? There is a force, gravity. Is there a torque, though? That's a toughie. Is there a torque? About what? Okay, let's say we're here. We're right here right now. Okay? There is a force acting on us of what? mg sine theta. Is there a friction? No, so A will change. V will change. Right? But Is there a torque? Guys? What? Yeah, Claudio, what causes rotation to change? Forces change speed. Torques change angular speed. Right? Normal force points into the thing. No torque. Is there friction? No friction. I need to explain what I'm asking. Is there a torque about the center of mass? What are the forces acting on the object? mg sine theta, mg cos theta, right? And we have what? Normal and force of friction, but that's zero. There is no torque about the center of mass. Okay? What are the other forces? You got mg cos theta, and you have normal. And none of them exerts the torque about, because why don't they exert the torque about the center of mass? So some of the torques about the center of mass is zero. Why? Because there's no friction. It's a frictionless surface. In the red, we have no friction. So what's going to happen to rotation? Nothing's going to change. Now, a bit tricky. Is there a torque about point B though? What the heck is going to happen now? We have a conundrum. No torque about center of mass. So what does that mean? That torque is equal to what? That's equal to I alpha. So alpha is zero. So alpha is zero. No angular acceleration. The angular speed will not change from this perspective because the torque is zero. Yet if we take the torque about B, and B is the point of contact between the tire and the surface, we have torque, seemingly. Anybody awake in the class? Out of the 3 sections today, is anybody awake? Yeah. It exists. You cannot use approach B. Why? The prerequisite condition to use approach B is that that point must be stationary for a little bit. And because this is spinning, it's not going to be stationary at all. So you can't use approach B. No conundrum. We're good. So, okay. So now, angular speed then, we've established that the angular speed is not going to change. On this side, there is no torque about center of mass. So what is this going to look like energy-wise? Pay attention. We say on the way down, mgh turns into, you could do it in 2 different ways. 1/2 of down here, mvcm squared plus 1/2 ICM omega squared. You can do that, which is fine. And V equals omega R, so you can figure it out. Okay? Now, on this side though, okay, so that's fine. That's down here. And then over there, right, what's going to happen? What is the energy up here? Let's call, today I'm not going to use the Waterman approach. I'm just going to use mechanical energy 1, mechanical energy 2, mechanical energy 3. Okay? Assuming that is 0, I have mgh, right? Down here I have what? 1/2 mvcm squared plus 1/2 I omega squared. All right? What do we have up here? What's the energy up there? mgy plus 1/2 I omega squared. Because that is not slowing down. That energy is still in there. Okay? Can you find YCM now or Y? What? Yeah, same omega. Do whatever you want. Figure it out. Right? So you have enough to find H, right? Y. You have enough to find Y. Don't be scared. You do. Okay? All right? So the answer will depend on what this object is. It's a solid sphere. But you see now that we have, guys, up here, at the point where y, plus 1/2, okay, fine. See, this is y is what? Y max. What I'm indicated is what is the maximum height this will reach, okay? So y, by y I mean y max, at which point here, y max happens where? So you're going to get to the point where v is equal to 0, but omega is still, this object is still spinning. Omega is not equal to 0, right? So, and up there, you're going to have omega, non-zero. The energy of the object is not just mgy. You're going to mgy plus 1/2 I omega squared. And then you have to go out the math to, piece things together. And that's equal to what? mgy plus 1/2 I omega squared. Okay? So it's up to you what you want to do, really. It's up to you. You could simply say, guys, ignore the step in the middle. As Claudio pointed out, ignore the step in the middle. You get that mgy, if you want, is equal to mgh minus 1/2 I omega squared. But you need omega. Where are you going to get omega from? This equation. Okay? That will give you, how do you get omega from that? Well, what is V equal to? Because this object is rolling, remember, this guy is omega over R. Plug it in, get omega, plug it in here, we're done. Okay? So this is your... omega R, sorry. That is omega R, not omega over R. For V. If you do not think you can do this on your own, put your hand up. Okay, people next to them, tell them how to do it. You have 2 minutes. And Chloe, if he doesn't know what he's doing in 2 minutes, it's on you. I know you have some questions and you're a bit puzzled. That's fine, right? You can take this home and figure it out, okay? It's not the end of the world, right? So, how many, if you don't know how to do this, still put your hand up. Just 1, 2, 2 people, 3, figure it out. Come see me after, okay? But now we have a map that tells us what to do. Look, because we know this. That is known. Which means that we know this, right? And it's just a matter of math now. All right. So, moving on. What I'd like to do is, on this problem, we have rolling without slipping. This is a cylinder or sphere. Let's say cylinder because it makes sense. There is enough friction to prevent slipping. And this thing is going to get pulled this way. What is the acceleration of the mass? First step, free body diagram. Second step, approach A, equations of motion. Third step, approach B, equations of motion. You have a lot to write, a lot to do. So first step, if you have your free body diagram done, put your hand up. Okay, folks, free body diagram. Well, we have here normal force and mg broken up into mg cos theta, not to scale, and mg sine theta. We have tension T, different colors for the camera. Tension T, we call it what? T2, and that's T2 here, which means we have T1 here, and T1 there, and mg here, okay? And also, what am I missing? Which way is the friction going to act? We don't know, and it don't matter. Because if you think you know, you need to know, and you have the wrong direction, we're going to end up with negative sign, okay? So now, equations of motion. Pretty straightforward, guys. Sum of forces And picking down is positive. We get what here? I don't want to spend too much time on the signs. You have enough of that everywhere. mg for the mass, m. Where's Alex? Tell her her absence is noted. Jasmine gets. Yeah, okay. Where is she? I am not impressed. Tell her he's actually having a crisis right now. All right. So I need somebody to grab my pants. Yes. Oh yeah, this is all wrong. Thank you. People, really? You actually slept through this? It was. I would have loved to say it was done on purpose. It wasn't. It was just I slept through this. Okay, guys, this is mg sine theta, and this guy is mg. Thank you. Right. mg cos theta. Okay. What's wrong with you people? All right. All right, guys. We have a lot of ground to cover. Let's get to it. So here we have mg minus t equals to ma. That comes from some forces in y direction with vector picking down as positive. All right? And T1. Thank you. For the pulley, we have the thing spinning this way. So that's alpha. For the pulley, we say sum of the torques about the center of mass for the pulley. That guy, pulley. This is pulley. Okay? Is equal to ICM alpha. All right? So, and that's what? Alpha pulley. Because it doesn't have to be the same. What are the torques acting about the center of mass for the pulley? We have torque of T1 plus torque of T2 equal to ICM alpha. All right? So we pick this to be positive. That's what you indicate here. So torque of T1 minus torque of T2 equal to ICM alpha. Why am I spending time on directions? Because this is a rotation. It's justified. Okay? Translation you should know by now. Right? And this is R, little r, T1 minus R, T2 is equal to ICM alpha pulley. How many unknowns? There's going to be a lot today. Okay, guys? That's fine. Pulley's done. We go over here, and over here we have, I'm going to split the board up into two. Approach A and approach B. Now, you pay attention to approach A. Okay? You say some of the torques, or some of the forces in the x direction equal to max. And just because you pick that to be positive here, it does not mean you have to pick that to be positive that way. But it just happens to be the case that it makes more sense. Right? Nobody, okay, so we have, from that, we're going to end up with, according to this picture, which makes no sense to me. You guys want friction to be that way? Whatever. Tension minus mg sine theta minus the force of friction, static friction, is equal to ma, and this is m cylinder, right? So cylinder here. Sine is this way, cos is that way. Thank you, Jasmine. Right? Okay. Count unknowns. Can you take stock of how many unknowns you have so far? T1, and this is T2, and alpha cylinder, and alpha pulley, and a lot of stuff, right? And A of what? A of the mass. I'm counting 5 or 6 so far. Okay, so we need lots of equations. Right? So, all right, guys? And then we say what? Sum of the torques about center of mass is equal to ICM alpha. Okay? So what acts about the center of mass? That's why you know you're wrong now. Okay? How do you know you're wrong? You guys are wrong. Because likely, I'm not sure. It looks to me like if I take talks about the center of mass, this guy is helping that guy. Maybe it is the case, yeah? We don't know. There's no way to find out right now. You could, moments of inertia will dictate what's going on. Moment of inertia, slope, you know. But there is no easy way of finding out. And if I don't know, you probably don't know either. Right? So some torques, according to this picture, whatever acts this way is positive. So I have what? That's positive, that's positive. What exerts torques about center of mass? Does this guy know? That guy know? That guy know? So we have only the torque of friction and the torque of the tension, and they are RT2 plus RFS equal to ICM alpha. The rest of this is just being savvy with math. You have equations, you have unknowns. The difficulty here comes from what? We said that in a typical rotation problem, you plug everything back into the torque equation, right? But there's two of them. So it gets mucky. You can do it. It just gets a bit messy, right? Okay, so in picture A, we have, why are we doing this? Because in picture A, rolling motion is a combination of translation of center of mass plus rotation about center of mass. Okay? Now, finally, we need what? ACM, A cylinder, is equal to alpha cylinder R. Okay? Is there one more observation you can make about this? How is, guys, how is A the mass? Where is A cylinder, by the way? Is it the top or here? How does it relate to A mass? No. A mass is the same as A string, which is A top. Okay? So this is A. Pay attention, guys. You're liable to have fallen asleep a little bit. So A the mass is the same as A top here, and A the mass, which is A, is equal to 2A cylinder. All right? So is Mansour going to solve the system? No. No, you can do math on your own. I would never solve it that way. Why? Because, pay attention. Let me count unknowns. What am I trying to tell you? I would not do it that way because I'm smarter than I look. Okay? Guys, please count unknowns with me. Not please, count unknowns with me. It's an order. It's not a request. Okay? Anyhow, so 1 unknown, 2 unknown, 3 unknown, alpha pulley. Right? 3 unknown, 4 unknowns. Right? If I overcount, let me know. 5 unknowns, 6 unknowns, 7 unknowns. Right? Am I missing anything? Cylinder. Do I want to do 7 unknown 7 equation? Unknowns? I don't want to do that. Okay, guys? I do not want to touch that. Why did I acquire a little more unknowns that I would like to chew? Because I use approach A. In approach A, I have to pay attention, guys. When we do approach A, the canonical way of doing things, we say some forces, some torques, and A equals alpha R. But some forces introduces F, an unknown, which I don't necessarily need. And some torques introduces the unknown as well, which I don't really need. Okay? Is there a way for me to reduce the number of unknowns? Yeah. How? Well, approach B says, now, rolling motion is seen to be a combination of translation of center of mass and rotation about center of mass. That's approach A. It's fine. It's a bit more work. You can do it. You're taking linear algebra. Right. So now, approach B treats rolling motion like a rotation about the point B at the bottom. So this is point B, and I go and say sum of the torques about B is equal to I about B alpha. That's all I need, not 3 equations. All right. So what is exerting torques about point B? Does Fs? No. Mg cos theta? No. And no. I have 2 of them, 1 and 2. So torque of, I will do this fully, torque of mgx plus torque of tension T2 in vector form equals to I, B, alpha. This is for the cylinder, right? I cylinder about B. C should be at the top. Right? And this is what now? One is positive, one is negative. How do you pick positive? We go like this. Okay, so torque of tension T2 is positive, minus torque of mgx is negative equals to I, B alpha of cylinder, and that becomes torque of, now, guys, on your own, plug in the appropriate things in there. What is the torque of the tension T2? How big is it? Not R, 2R. How far is it from the pivot? Tension of T2, this is the pivot. This is 2R. Right? 2R. So 2R T2, right, minus, how far is mg from the pivot? Mg sine R, mg sine theta equals to I about B of the cylinder alpha. Okay? Now, how many unknowns are there here? I've killed F. F is no longer an unknown. We make things a little bit easier, a little bit better. Okay? So, all this said, what is, do you want to come here? Okay. Guys, how would you get the final answer to this? You have to grind. Put things down, I'll give you the final answer so you can check it at home. Now, how does Mansoor get the final answer? No? Okay. Approach C. All right. All right, so if you think that it's a cheat to use energy and it's easy, go ahead. You come up with the right answer, you get a piece of baklava too. All right? All right, you guys have 3 minutes to arrive at energy answer, okay? But let's do that later because I want to do something. So Josh is still leaving, right? At some point? What? For the whole thing? So we will go back to that one there and we'll do the energy approach. But before that, can we do this problem first? And this one we are going to get the answer from forces. You could do it with energy, but first do it with forces and torques and see if you get the answer. First of all, draw on your own the free body. Now you have to separate things, okay? You can't keep them together. You gotta draw a block and 2 cylinders beneath it. Separation. Draw the free body diagram of each object. Full free body diagram of the blocks and each cylinder. Block, yes? Guys, what do we know? Well, we're pushing this with F. There is a normal force here. And where's Alex? Somebody text her, tell her to come grab the pens. So this is N. This is N. Okay. And, you know, this action-reaction pair, there is N down here as well. There is N from the ground. There is N from the ground. And there is a force of friction. Do I know which way it acts? You might want to guess, say this way or that way, but really you don't. It depends on a lot of stuff. Okay? I'll show you why in the example after this. I know for a fact, though, that these guys, Tony, are being pushed this way, right? Yeah? You are awesome. Thank you. Okay? I don't have candy. I would have given you candy. Tell her, A, he's hurt. B, you need to be here. What? Tell her Mansoor says he's hurt. And B, you need to be here. I will. All right. Okay, so force of static friction pushes cylinders that way. So same thing happens that way. Reaction pair. Right? And what else? Force of friction from the ground. I don't know what it is, what points, rate points. But I have maybe, I don't know, this way, let's say. I like to think it's this way. Fs ground and Fs ground. Okay? You may disagree, but it won't matter. Why? Because we're going to use approach B. Why do you use approach B? Because we don't want to worry about the force of friction on the ground. There is enough to worry about otherwise. Okay? Now, guys, it's very simple. Next step is write down the necessary equations of motion. There is only 3 of them. One for the block, one for the cylinder, same for both, right? And one for E equals alpha R. Okay? If you write it down correct, you will likely pass the course. This is your chance. If you write down the correct equations with all the bells and whistles, you will likely pass the course. So mg, thank you, m block G, and m cylinder G. The fact that I forgot it indicates what? It don't matter. When does it matter? The only time it matters is when they tell you that one thing is about to slip or something like that. But we have no slippages. You know, we don't know that things are about to slip. If we do, we know that we need the mass. Folks, I will do this to a conclusion. I'm really not interested in solving 6 equations, 6 unknowns. You guys can do that. There is no point. You know, this is not an algebra course, and I'm not bringing you here to do half an hour of algebra. This is not, I don't know how to do it. I'm just kidding, I do. And honestly, guys, this is a problem on Mobius. The solution is provided for you. When you go and screw up, it gives you the right solution, right? Yeah. That's what I've been doing all term. So just screw up and find out, okay? All right, folks. So, guys, for the block, sum of the forces F minus 2 Fs equals to M block A, right? F is given. A is what we want. How many unknowns? 2 unknowns. All right. For the cylinders, am I going to use approach A or approach B? I mean, you can use approach A if you want, but just too many unknowns. For the cylinders, so cylinders, approach B says what? Sum of the torques about point B is equal to I, B, alpha. I will do a full solution for this one because I can. I know how. Guys, pay attention. Where is point B on the cylinder? Right there. Okay. What exerts torques about point B? mg. Right, indeed. So not this, not that, only, and not normal. Lots of forces. Only Fs times 2r. Times 2r. Did we call it big or little r? I forget. Same thing. 2r. Equals to, what is I about B for a cylinder? mr squared over 2. See, I'm actually doing numbers or whatever. Plus mr squared alpha. So Fs times 2r is 3/2 mr squared alpha. All right? How many unknowns? 1, 2, let's not double count. 3. How many equations? Equation 1, equation 2. What does equation 3 say now? A equals to, because we're rolling, alpha r. If you are okay with this, you just lost half the mark for the question. For the whole question. Yeah. That is ICM plus MD squared. All right? So, high five. Thank you for that. Okay? So, guys, if you are happy with this, you will lose a lot of marks here. Okay? What A is this? Yes, it's true, guys. ACM of the cylinder, that guy is indeed ACM is alpha R. But what is A? What did we reserve A for? Acceleration of the block. That's the same as top of the cylinder. That is 2 alpha R. All right? Now, this is a doable problem. What do? We substitute everything into the torque equation. All right, guys? I will actually do it, and hopefully I won't make a mistake. Right? So, people, Fs is what from here? Fs is, help, F minus MBA over 2, right? Times 2R. Yeah? Is that right? Is equal to what? That is equal to 3/2 M R squared. Now alpha is what? Alpha is what from here? A over 2R. Okay? Now from that, and it's all, okay, so M what here? M block, M cylinder, right? Don't mix up the M's, guys. This is M cylinder, M cylinder, M cylinder. Okay? Could somebody give me what A will be from this? That's the limit of my math, guys. I've done plenty for you. Sarah, you have it? A is equal to F over 3 over 4M plus, are you sure? This is A of what? A of the block. Okay? All the rolling problems you have done so far, you had in all of them rolling without slipping. Right? So, nothing involved except for the first one. That was a bit of slipping there. So, rolling without slipping is like this. Okay? So now what happens if you do this? You have a bowling ball, and you let it skid first, and then, So it's skidding. Omega is 0 initially, and you have VCM, and then, okay, let's go over it one more time. All 3 sections have seen this so far, the demo, okay? So let's think about it one more time. I don't want any water will increase the friction, so trying to minimize that. Okay, so guys, we're going to do this 2 different ways. I'm going to teach you a really cool concept today, or at least start the concept. Maybe we can finish it off in the lectures if we go for too long, okay? All these rolling problems are the most intense you've seen so far. We cannot zip through them, and you understand now why I was not doing the algebra. If I want to solve 7 equations, 7 unknowns, we'll be here till 12 o'clock. You got better things to do. Maybe I don't, but I'm sure you do. All right, so guys, check this out. You have this object skidding originally, and then it rolls eventually, okay? So you see, so as it's skidding, skids, and then rolls. What now? It's not. It skids and rolls slightly, and then rolling. The rotational speed picks up until we have rolling. When we have rolling, V is equal to omega r. Right? So what force is acting on it as it skids? What kind of friction? Kinetic friction, because it's sliding on the surface. Okay. So what is friction doing to the? What is friction doing to the speed of the center of mass? Slowing it down. Yet at the same time, what is it doing for the rotation? So rotation will pick up, and the translational speed will go down until we have a matching V equals omega r, at which point this will roll. Now, I mentioned to you before that the speed, when V equals omega r on a flat surface, if you have an object rolling on a flat surface, like that, and it's horizontal, it's counterintuitive, but the force of friction is indeed 0 at that point. All right? The force of friction will be 0. Okay, so that's one thing. So that's skid, then roll. The other one is what? Roll, then skid, like this. Well, do that. So Scooby-Doo maneuver, right? So we go like this. Yeah. It's not easy. Yeah. Dang it. It's a funny bottle. Thanks, Adam. Yeah. All right, there you go. Okay. So, okay. So, yeah. Thank you. Finally worked out. So, you need something homogeneous, and this is dent in it on this side. I know what you've been doing with the bottle, but okay. So, it's spinning, guys. Which way is it kicking the table? It's pushing the table back. That's why it kicks the table back. Table kicks it forward. That's why it goes forward. 2 things happen. The force of friction, as it's spinning this way, the force of friction points that way. It causes it to speed up, but causes the rotation to slow down. Okay? So until we have V equals omega r. And then you have that topspin. It's called topspin because backspin is like this. Right? Okay, how do I do this? Oh, one more time. Yeah, a kind of backspin. Right? And if you're lucky, you can just get it to do stop. Maybe, I don't know. Okay? So that'd be an interesting, very interesting final exam problem. Hint, hint. All right, so we will do at least one version of this, okay? 2 ways, guys. So your ball is originally skidding. So VCM is whatever it is, and omega is 0. This will be acted upon by the force of friction until it gets to the point where it's actually rolling. All right? So if it's a ball of mass m, and give this to Alex. Good catch, Tony. You saved me some trouble. All right, okay, so omega equals 0 initially, omega initial, and VCM is not 0. All right? This is acted upon by the force of friction and omega will pick up, V will slow down, so V goes down, and omega picks up, goes up, right? Until we have V equals omega R. This is now rolling, no slipping, okay? So the question is, guys, how much time does it take for this thing to roll? How much time does it skid? Also, how long does it mean? How much distance does it skid over, right? How long does it skid for? D is what? And finally, maybe how many rolls, turns does it go through, right? So you have the mass, you have the coefficient of friction, right? Or actually, finally, guys, what is VCM when this thing rolls? Okay, so again, so this is real, right? The nice thing about rolling motion is that it's complex, but you're dealing with stuff that is real. You can actually see that. You can grab a bowling ball, bowling alley, and you can calculate, something. It's not really massive, complexity, but it's the first real kind of application you can see in real life. All right, guys, take a few minutes to set it up. How would you do this? What is the velocity of center of mass when this is rolling? Okay, it's a tough one, okay? So let me start working on it. So we'll do it one of two ways, right? What is the only force acting on this thing? Friction, so Fs, right? There is also what, mg and n. Yeah? F kinetic, yes, thank you. F kinetic. Okay, so we have what? The velocity is going to change according to V minus AT, or basically velocity as a function of time is going to be AT plus V naught in vector form. Let's just do it scalar. It's easier. We don't have to go into details. Find a pen that works. Okay, so velocity as a function of time starts at high, which is V minus AT. Right? All right. Okay? And what is A? How do I get A? Well, sum of the forces, which is really only F kinetic, equals to MA. Therefore, A is F kinetic over M. And what's F kinetic equal to? N mu K over M, and that's N is mg mu K over M. That is equal to G mu K. All right? The acceleration is, pay attention now, force divided by mass gives me acceleration. That is how the speed is going to change as a function of time, velocity. Right? So V is equal to V naught minus AT. And V naught is the speed we had to start with, if you want. All right? Okay, so if A is equal to G mu K, why is that again? Because A is the force over the mass, the force is N mu K, and N is mg mu K over M, G mu K. Check. Now, guys, it's pretty easy. So V is going to slow down according to that. Omega is going to pick up as omega naught plus what? Alpha T. All right? And omega naught is 0. Okay? How many unknowns do I have so far? V and T and omega 3. Right? What is alpha equal to? If A is G mu K, what is alpha? A equals alpha R, right? So A is, alpha, that alpha is what? G mu K over R, because it's rolling motion, right? Are you all okay with that? You just lost half the mark. That is only true if there is rolling without slipping. This problem is about slipping. You can't do that. We don't know what alpha is yet. Okay? You cannot use that because A, guys, A is not equal to alpha R. This is not, like, okay, check it out. The rotational and translational are not related by V equals omega R. V is whatever, omega is 0. We have no reason to believe that this will hold. A equals alpha R. It won't hold, as a matter of fact. Okay? So how do you find? So what do we have? The solution is right in front of us. We have omega naught. We have that. We have A, which we just calculated. How many unknowns do you see? 1, 2, 3. Right? Assuming that we know alpha. And then we need one more equation, which is easy. How do you get alpha? Guys, look here. Alpha is what? Torque is equal to torque about center of mass. That's the only thing we can do is ICM alpha. Right? So alpha is torque center of mass divided by ICM. And this is, let's say, what? Bowling ball. So this is a solid ball, let's say. Okay? So alpha is, what is the torque? The force of friction times R divided by ICM 2/5 mR squared. All right? We have the force of static friction, which is equal to what? Kinetic friction, sorry. Kinetic friction. It's a long session. I'm starting to lose my beans. Okay? So, guys, what is the force of kinetic friction? N mu K. And that's equal to what? mg mu K. Right? So, that alpha now is mg mu K R divided by 2/5 mR squared. So what is alpha from that? So this is wrong. Right? Alpha is mg mu K R divided by 2/5 mR squared. That becomes what? 5/2 G mu K over R. That is, it's not A over R. It's not G mu K over R. Okay? Now, this will be different for a cylinder than it is for a ring, than it is for a sphere, disc, whatever. Right? So now, what do we have? We got V is going to increase or decrease according to V naught minus G mu K T. That's V as a function of time. Right? It's going to drop. Omega is going to go up as alpha T. That's equal to what? Alpha is 5/2 G mu K times over R times T. All right? That's omega as a function of time. Omega is going to increase. V is going to decrease until when? Until they are what? V as a function of time becomes equal to omega R. Why is that the case? Because we have rolling. All right? So we'll plug those in there. All right, guys? V equals omega r. So V naught, that's V up there, minus G mu K is equal to omega 5/2 G mu K T over R. All right? Yeah. T somewhere. Where's T? Yeah. T. R times R. Okay? What am I doing here? Omega times T. Yeah. V is equal to that. T. Yeah, that's fine. I think we're good. You don't need R. Actually, you won't even need mu K, you'll see. Okay, so guys, so what have we done so far? We have, it's not that complicated. The only force acting on this is friction, kinetic. mg mu K. You divide by m, you get A, G mu K. The only torque acting on it is R times G mu K divided by a moment of inertia, you get alpha. So we have V going down according to this, and that's A, that's your A. So, and omega is going up according to that. Until we have what? Rolling motion. One goes down, one goes up until V equals omega R. All right? So what do I get from this? Guys. You can solve for what? T. So could somebody give me T? What is T equal to? V naught over G mu K plus 5/2, what? R's cancel, G mu K. Really interesting, right? The time is T is equal to V naught over, what is that? 7/2, so 2 7s, right? Is that right? V naught over G mu K. Okay, folks? All right? So what did the question want, though? The velocity at the end of this business. All right, so what's the velocity equal to? V is equal to V naught minus AT. Can you work out the answer for me, please? A is G mu K, and T is what? 2V naught over 7G mu K. So G mu K is cancelled, and this is what, guys? 5/7 of V naught. Guys, it's really interesting. It does not depend on mu K. So whether you slide it on cotton or ice or whatever, you're going to end up with the same answer in the end. It doesn't matter if you slide on carpet, on wood, on whatever. Okay? So V minus AT, omega alpha AT until V equals omega R. Okay? Cool? So this one is straightforward. You just do kinematics, forces, and decrease V, increase omega, till you find T, and then you solve it. Now, this problem is doable in using, you pay attention, it's going to go over your head. We can use one of the conservation principles for this one. Not conservation of energy, why? Because we have friction, kinetic friction, changing the energy on us, right? So now guys, this is skidding, no rolling. And here we get to the point where after a while, after distance d, this is going to roll without slipping. Pay attention. energy is not conserved. Guys, but if I choose this point here, this is very specific. This is point A. The point at which this wheel starts rolling. Okay? So the wheel skids, and at this point it starts rolling. So, Kim, I'm going to take, don't freak out. I'm going to, pay attention, guys. I'm going to say that, take this point, all right? What is the only external non-zero force acting on the object? Normal cancels out with gravity. You have what? What is left? Friction. Can you see where I'm going with this? First person to see this, I swear, I'll buy you lunch. Guys, the only force acting on this is the force of static friction or kinetic friction. F kinetic. Right? Okay? So the only force acting on this is the force of kinetic friction. This object, well, can I say the following, guys? The torque, the only force is what? Friction. The torque of friction kinetic about point A is equal to what? What's the torque of F about A? Does this, in principle, if you have a pivot here, right, and you have a force pointing in or out of the pivot, does it exert the torque about the pivot? No. The torque of F about is 0, right? The torque about A is 0. What does that mean? This is torque net. And if torque net is 0, what is torque net equal to? Tau net is what? dL by dt. And that's about point A. That's about point A. What does that mean? The change in momentum about A is 0. Angular momentum. So L, this is situation 1. Situation 2, this means that L in situation 1 about A is equal to L in situation 2 about A. All right? Fair enough? Guys, what is L in situation 1 about A? We have an object moving in a straight line. All 3 sections should know this. If an object moves in a straight line, what is the angular momentum at a point? R cross P. So R, pay attention. Initial momentum is R cross P. Okay? So initial angular momentum is L initial about A is equal to L final about A. And initial about A, I have no spinning. Okay? It's just, had there been spinning, you have to add that too. This is called spin orbital angular momentum. Okay? I hinted to it because Earth does what? It orbits the sun, but it does what as well? Spins about the sun. They both contribute to the angular momentum. You just add the two. Here, LCM plus L, yeah? I'll show you that in lectures. Okay? So we can use that if you have the ball spinning first. Okay? If you want to solve the ball spinning first, you can do it with that one, but you can do it with angular momentum, but you have to incorporate spin orbital, which we haven't used yet. All right? Now, this guy, L initial, is simply, this is moving in a straight line. L initial is equal to what? R cross P. R, P sine theta. Reduces to what? R, P sine theta is equal to R, M, V. Naught. This had velocity V naught. All right, guys? So the initial angular momentum is simply R, M, V sine theta, which is what? R, so it's equal to initial angular momentum is L initial is RMV sine theta, and R sine theta is simply in that triangle R, and that's RMV. Right? Now, what is the final angular momentum about point B, point A? No, what is angular momentum equal to? I about A omega final. Yeah, because what? L, for a rotating object, guys, don't forget that the angular momentum is equal to I omega. Right? Angular momentum is always I omega for any rotating object. And in this view, guys, when we look at rolling motion as a rotation about point A, then if you have a spinning object, L is I omega, right? Only when the object is moving in a straight line, you use R cross P. When it's spinning, it's I omega. So this is now a spinning object about the point at the bottom, right? And what is that equal to? I about A is what for a sphere? 2/5 mr squared plus mr squared times omega. All right? Look at that. One liner. We have the solution. What is omega equal to? Omega, when this starts rolling, is equal to what? Right here. This is omega here. Now omega is equal to what? Omega is equal to, hold on, R M V naught over 7/5 m r squared. Right? All right, guys? So VCM, because it's rolling now, is omega R, and that ends up being what? Five sevenths V naught. Okay? All right? So you have used angular momentum to solve a very complex problem in one line. All right, folks? I'm reaching the end of my rope. I'm sure you are as well. You've been troopers today. Thank you so much.